Welcome to topic 4.3. In this topic, we will learn about chiller plant optimization as well as the different ways of achieving coolings other than using a typical chiller. For chiller plant optimization, why are we so concerned about trying to optimize what is being consumed by the chillers? As you can see from this pie chart, around 50% of the energy is actually being consumed by the chillers compared to the pumps, AHUs, and cooling towers. So any modification, if you do any changes to the chiller, imagine the amount of savings you can achieve. Okay, just by tweaking a bit of the parameters or trying to adjust some of the set points to make sure you make it operate at the most efficient manner. So let's focus on a chilled water loop first. For chilled water loop, right, one of the strategy we can use is try to increase the chilled water supply temperature. This is nothing surprising, okay, because as we know, if your chilled water supply temperature is not as cold, for example, initially, right, your CHWS temperature is 6.5 degrees Celsius. If you try to increase this chilled water supply temperature to maybe 8.5 degrees Celsius, you will achieve significant savings in the chiller itself. Why? Because your chiller will not have to work so hard in order to cool down the water. So it's like what we have learned in topic 1. If you use a pH diagram to explain your answer or explain this savings, is because your evaporating pressure is now shifted up. So basically you flatten your pH diagram, the trapezium, so the suction pressure will increase. And the pressure head, which is delta P, okay, between the condensing pressure and the suction pressure, evaporating pressure, that is the pressure head, it will reduce. So when this happens, your chiller efficiency will improve. And the rule of thumb is every 1 degree Celsius increase in CHWS temperature, your chiller efficiency will improve by 2%. So energy consumption at the chiller, okay, at the chiller will reduce. So what is the negative aspect? Okay, why don't we just increase the temperature to very, very high? Okay, why can't we do that? Because whenever you go and adjust this temperature, the chilled water supply temperature, it will have a very drastic effect at the AHU side, at the air side. Because you imagine now at the AHU, the water is not as cold. So when the water is not as cold, your fan may have to work harder, okay, in order to bring down the temperature. So because of that, your off-coil temperature will increase. That means the temperature after passing through the cooling coil will increase because your water is not so cold now. So your space temperature and humidity will increase. And because of that, your VAV box will all start to open and your fan speed will definitely increase. So all in all, although your chiller is saving a lot of energy, okay, but your AHU side will definitely be consuming more energy. So doesn't mean that it's good to increase the chilled water supply temperature. You can do it, okay, without other consideration. Okay, so you should increase to a point where your AHU is able to handle the increase in temperature as well as the thermal comfort. The comfort level, thermal comfort is not compromised at the air side. So usually the highest it can get may be around only 9 degrees Celsius. Okay, usually you cannot go higher than that. So that's one of the strategy. The second strategy is trying to reduce the condenser water supply temperature. Condenser water supply temperature is also known as entering condenser water temperature. So that is the temperature of the water when it comes out from the cooling tower. So we know that it's good if this temperature is low, because if it's low, you are able to cool down the condenser more. So if you are able to remove more heat at the condenser side, your condensing pressure will drop. So similar to what happened just now, the trapezium will be flattened. Okay, the pressure head will reduce, your delta P will reduce, and your chiller efficiency will improve. So again, energy consumption at the chiller will reduce. But of course, there's always a downside. So what's the downside? Before we know the downside, you have to know how to actually achieve a very low ECW temperature. So in order to achieve this, you have to try to reduce the approach temperature. As I mentioned in the previous topic, approach temperature is the temperature difference between your condenser water supply temperature and the ambience wet bulb temperature. So we always try to supply a water temperature that is very, very close to the wet bulb temperature. So the first law is, this temperature is always limited by the ambience wet bulb temperature. Okay? And your cooling tower fan speed, right, has a direct effect on this temperature. The harder your cooling tower is working, the lower it can bring down the temperature because of the evaporative effect. So when fan speed increase, more heat will be removed because you have higher rate of evaporation. You are inducing the evaporation. So when there's more evaporation, there will be more heat being removed, and your condenser water temperature will drop and nearer to the wet bulb temperature. So you imagine if you have a curve like that, this is your wet bulb temperature, and this is your entering condenser water temperature. If you increase the fan speed, it will start to tend towards the wet bulb temperature. And of course, the best scenario is your entering condenser water temperature is the same temperature as your wet bulb, because this temperature will never cross the wet bulb temperature line. Okay? And the gap between this part is your approach temperature. So this part is actually, the gap here is your approach. So the best is you can reduce this approach temperature as much as possible in order to have a very low entering condenser water temperature. So what is the good thing about having very low entering condenser water temperature? Of course, like what we mentioned just now, the chiller efficiency will improve, energy consumption at the chiller will reduce, but of course the bad thing is your cooling tower will have to work very, very hard. Your cooling tower, you have to increase the speed very much, okay, until it is very near to the ambient wet bulb temperature. And during a hot and humid day, let's say your wet bulb temperature is shifted up, no matter how hard your cooling tower is working, it will never achieve a very low entering condenser water temperature, because it's always limited by your weather condition. So we have finished with the chilled water side. Now let's look at the condenser water side. So condenser water side, one of the things we can do to optimize your chiller is to maintain your condenser tubes regularly. Because condenser water load is open system. What do I mean by open system? That means your water is actually being exposed to the outside air. So you are exposed to all the impurities, all the dust particles. So fouling and scaling at the condenser tube will be very common. That means there will be a layer of scale that's attached to your condenser tube. So when that happens, your heat transfer efficiency will drop a lot. So you imagine you have a condenser tube. So let's say you have a condenser tube. So by right, cold water is here. Your condenser water is inside. And outside is your hot refrigerant. So what you are trying to do is to cool down the hot refrigerant, okay, by having heat transfer between the cool condenser water and the hot refrigerant. But if there's a layer of scale that is forming, so heat transfer cannot take place effectively. Okay, and because of that, your refrigerant, when it leaves the condenser tube, it will still remain very high temperature, and this will cause your chiller to deteriorate, okay, the efficiency to drop a lot. Okay, so every 0.6 mm of scale that appear at the tube surface, it will cause an increase in 20% of power consumption in chiller. So it's very important to maintain the tube regularly. That means you have to clean the tube regularly. But to do that manually is quite difficult. Okay, so there are a few ways to do that. First, you can use water treatment. You try to remove all the impurities at the water okay, by using chemical to dissolve the impurities. Okay, if not, you can use blow down method. That means time to time you remove all the water, or maybe partially, okay, 50% of water, and you top it up with clean water, okay, or new water without impurities. Okay, so that's called blow down. That means you dilute the concentration of impurities. Then the last method is try to clean the tube at a regular interval. So the challenges for water treatment and blow down is for water treatment, right, is it cannot eliminate the scaling completely. Okay, there's a limit that this chemical can work. Okay, and for blow down and tube cleaning, you will see this kind of pattern appearing, a sawtooth kind of pattern. That means whenever you clean your tube, your efficiency will improve. Okay, but your efficiency will deteriorate, okay, over time. And when it's reached certain limit, when you think that it's time to do a cleaning again, then it will improve again. So that's some of the challenges that you may face if you want to clean your condenser water tube. The other very common method nowadays is using automatic tube cleaning system. So how do they do that? They do that by introducing very small balls, okay, ball type of cleaning agent introduced into condenser water. So imagine when this ball, okay, rub against the surface of the tube, okay, it will sort of clean it at the same time when it's flowing. So one is using the ball method, the other one is using brush method. So these are the two common kind of automatic tube cleaning system available in the market. Okay, now I will continue with the optimization strategies for pump and fan system. That means for system with motor drive, okay, that transport your fluid around, be it water, condenser water, chilled water, or your air. So these are some of the area where you need to use pump or fan. There is your chilled water pumps, your condenser water pump, cooling towers, and AHU. Although individually, right, they do not consume much, but because there's a large number of them, you can easily have up to 20 to 30 AHU or 50 to 60 FCU in a building. And chilled water pump is used sometimes, let's say you have one chiller, you may have one chilled water pump and one condenser water pump. And cooling towers, sometimes one chiller is to two cooling towers. So all this, when it add up together, is quite significant. It contributes to the other 50% of your energy consumption. So the best way, okay, one of the way that to reduce the power consumption in pump and fans is to reduce the losses. Okay, losses when your fluid is moving. This can be achieved by having maybe a larger pipe, okay, minimizing your piping length, reducing sharp bends. So all this will reduce your minor losses. Okay, when the minor losses are being reduced, okay, there will be less friction, there will be less turbulence. So your fluid will be able to flow more, so-called smoothly, and there will be less wastage in terms of pressure loss. So that is one of the method. Second method is always try to avoid oversizing the pump or fan. Because if you oversize the pump or fan, and if you want to reduce the flow rate, you have no choice but to use a valve. So for example, let's say you have a pipe, and it is this pipe is capable of producing a flow of 60 liters per second. Okay, but because you do not require such a high flow, that means you have already oversized your pump. Okay, you only require maybe 30 liters per second. 30 liters per second of water. So what you do, you will start to close the valve to maybe 50%. Okay, close the valve 50% close, such that only half of the water will be able to flow through. Okay, so if you do that, a lot of losses occur over here. A lot of pressure losses occur over here. So it will be better that you size the pump correctly, such that your valve is, this one is 50% open. So if you are able to size your pump correctly, you should have 100% open valve. And your water will just flow through without much obstruction. In that way, your system curve will be so-called much smoother. Okay, and the area under the graph, okay, will be smaller. So if that happen, if you always oversize your pump, usually your system curve will be pushed up, okay, and it will consume more energy. Okay. Then the third method of trying to optimize the pump and fan is using a high efficiency pump. Okay, so that means you have to choose an impeller that's able to generate the flow, okay, with a better fluid. So all this, it depends on the type of equipment that you select. Or also a high efficiency electric motors. So usually motor, right, you will have to size it correctly also. So other than sizing the pump correctly, make sure you also size the motor at the correct size. Okay, so if your motor is sized correctly, it will operate at always near to 100% of its capacity, and that will be the best efficiency that it can have, around 80 to 100%. Okay, so if you undersize it, you can see from the graph that the motor efficiency will deteriorate a lot. So ensure that you size your pump correctly, ensure that you size your motor correctly, and make sure you have a high efficiency pump. Okay, these are the few methods. And the last method you can use, let's say you have sized your pump, but because over the years, maybe the load changes and the requirement changes, you may not need such a high speed anymore, high flow rate anymore. So instead of using a valve, okay, to reduce your flow rate, what you can do, right, is to install a variable speed drive, okay, or VSD. So what does variable speed drive do? So variable speed drive is attached to the motor. So what it does is, it will reduce the motor speed, okay, adjust the frequency such that it will generate a lower RPM. Okay, so a VSD can be installed there, but it will actually, this VSD is actually quite expensive. Okay, it can easily cost up to 3 times the AC motor. So, but this strategy is much better than trying to use a valve to reduce the flow rate. Why is that so? It's because of this fan law. Fan law, or sometimes we call it the pump affinity law. So this law, right, it tells us, it highlights one important point. That is, the power consumption of a fan or a pump, okay, is not directly proportional to the RPM. So what do I mean? So for example, if your pump, okay, original speed is equal to 500 RPM. Okay, let's say this is your original speed. And let's say you adjust the speed, okay, new speed, you increase to 800 RPM. Okay, there's a 60% increase of speed, but the power consumption will not increase by 60% only. That's the problem. Okay, so although your pump speed increased by 60%, you increase another 300 RPM, that is 60%. Your power consumption, let's say initially is 20 kilowatts. The new speed, with the new speed, the power consumption will not be 60% more of the 20 kilowatts. In fact, it will be 60%, okay, to the power of 3 multiplied by 20 kilowatts. That is to say, because of this cube law over here, this last equation. Okay, so the new power divided by the original power is equal to the new speed over the old speed to the power of 3. So as you can see, the reverse will also happen. Let's say you reduce the speed from 800 RPM to 500 RPM, the power will reduce much more. Okay, it will be the energy savings is much higher, okay, than the percentage savings in the speed. Okay, so it is not linear. That's why this is one of the very popular strategies nowadays. That means you may operate multiple cooling towers, but all of them you throttle to a lower speed. Then you will achieve some savings.